Hello, everyone. Thank you for being part of today's digital CCIS seminar. As mentioned already, I'm a PhD candidate here at IIK, working under the supervision of Stephen. I'm also a member of Critical Infrastructure, Security, and Resilience Research Group. I'll be presenting one of our research outcomes titled Modeling Adversarial Flow in Software-Defined Industrial Control Networks using a queuing network model, which was presented at IEEE Conference on Communications and Network Security that was held in France, July this year. Before proceeding with this presentation, I would like to tell you a bit of my background. I am originally from Nigeria. Before moving to Italy for my master's, I have worked in the IT industry for more than 5 years. The last position that I held was as a computer consultant with Renaissance University and Miamata Elizabeth High School, all in Enugu, Nigeria. I left Nigeria in 2016 for a master's program in computer science with specialization in networks and security. During my master's, I also obtained a micromasters in cybersecurity from Rochester University in New York. And also I undertook my master's thesis at Royal Holloway, University of London. I completed my master's in 2018, finishing with summa cum laude. And then I worked briefly with Cisco with the next generation firewall team at Krakow, Poland. That is before joining NTNU last year, February, as a PhD candidate. It has been an amazing journey for me, and I'm so happy to be presenting one of our research outcomes today. The outline of this presentation is as follows. First, I'll give a brief introduction. I would also discuss SDN and why there has been a growing interest in its application in several sectors. The problem that was investigated in this work will be discussed, and some related works will be described. Then the system that was modeled in this work and the performance measures used will be presented. In addition, the developed model will be used to evaluate adversarial flow in software-defined industrial control networks. Lastly, I'll conclude the presentation and present future works. So let's begin with the introduction. During the first wave of COVID-19, that is between mid-March and May this year, there was a surge in internet traffic due to the lockdown that was imposed on several parts of the world. AT&T reported that it was able to accommodate this internet COVID-19 traffic demands with the help of SDN and network function virtualization. This is because SDN enabled it to dynamically scale up its network infrastructure to keep pace with the rising internet traffic stemming from the COVID-19. With the traditional networking infrastructure, it would have been impossible to achieve this feat. This further demonstrates the importance of SDN and also justify the growing interest in applying SDN in other sectors. The question some of us might be asking, what exactly is SDN? So that is the question we'll try to answer in the next slide. SDN is a networking architecture in which the control is separated from the data plane. The network intelligence is also centralized, and the state of the system is logically centralized too. And we have that the underlying network infrastructure is abstracted from the application. In the traditional network architecture, the control and the data plane are embedded on the networking device. However, SDN took a different approach by opening up the networking infrastructure, as will be depicted in the animation that we'll be showing now. So we have this. The main objective of SDN is just to simplify the deployment of control functions and to support the applications with applications to deal with single abstracted network environment without regards for the implementation details. In addition, lowering the dependency of proprietary components. Therefore, SDN enables network functions to be directly programmable, which facilitates the automation of network functions and the building of highly scalable and flexible networks that can quickly adapt to changing environments. In general, a typical SDN architecture consists of the application layer, the control layer, and the network infrastructure layer, or it could also be called the network layer. The application layer is responsible for sending applications requests for network to the control layer, and this interaction is accomplished via the northbound interface. The control layer translates applications requirements and exercises control over the network devices while providing the required information to the application. Also, the network layer is made up of network devices which interacts with the control layer via the southbound interface. The implication of this setup is that the network intelligence is logically centralized in SDN controller, which provides increased visibility into the entire networks. Hence, the network would appear to the application and the policy engine as a single logical switch. Therefore, network devices no longer need to store and process several protocols, but rather accept instructions forwarded to them by the controller. So what exactly is the problem that we tried to solve in this particular work? The question that we had to ask is, can SDN be used in industrial control networks? Now, we've seen that recent advances in networking technology have witnessed a gradual shift in industrial control networks from serial-based communication to Ethernet communication. This provides the opportunity of exploiting the benefits of SDN for industrial control networks because the correctness of industrial control system protocols rely on the guaranteed quality of service. However, SDN not only offers benefits, but also raises questions about the ability to guarantee the quality of service in the presence of adversarial flow. So what exactly is this adversarial flow? Adversarial flow is an additional flow, usually malicious, that may be introduced into the SDN architecture by an attacker. The arrival rates and the service time distribution of adversarial flow can be manipulated by the attacker to achieve his desired aim. So we have actually described this idea of adversarial flow in our previous work, which was presented at International Conference on Computing and Computing, Networking and Communication that was held in Big Island, Hawaii, earlier this year. So what we did in this work, we actually surveyed the existing literature on the use of queuing network models. What we observed is that queuing network models have been employed in the literature for the performance evaluation of different applications of SDN architectures. The approach that was adopted by several of these authors involves the use of well-established results from queuing theory to study the interactions between the forwarding plane switches and the control plane controllers. Although it is possible to also use simulation and experimentation, but analytical model allows for a wider study of different configurations of this SDN architecture. Now, what we also notice in most of the study is that none of them has considered a situation where an adversarial actions could occur. And as we mentioned, adversarial flow is the additional flow, usually malicious, that can be introduced into the SDN architecture by an attacker. So the main goal of this work is, first, we proposed an analytical model for software-defined industrial control networks, which considers the strong periodic patterns of network traffic in the data plane. Then we use this model to study the effect of adversarial flow in software-defined industrial control networks. Now, what this provides us is that it helps us get useful insights for benchmarking and facilitates the identification of factors that could cause the network to breach the stringent quality of service requirements. Now we are going to consider some of the related works. Now, it may interest you to know that the first analysis of SDN using queuing network was conducted by researchers at NTNU. So this work was presented by Jack Chirac et al. In 2011. Now, what they did was to focus on characterizing the interaction between the SDN switch and the controller. However, they did not consider any specific application of the SDN architecture. Other authors have also considered different features of SDN. The reference one here considered the trade-off between buffer sharing mechanism, right, using SDN, using queuing network models. And also the reference to him used a queuing network model to characterize the performance of hardware switches and software switches in SDN. And the reference 3 in this slide present the performance study of SDN switches using a queuing network model. And we have that the authors in the fourth reference here use queuing network model to study the performance of SDN with network virtualization function under or outside the controller. Also, SDN-based cloud architecture has also been examined using a queuing network model, as done in reference 1 and 2. Now, in the reference 2, the additional thing that was done was to use the queuing network model to consider software-defined network function parallelism in the cloud. And the author used this model for optimizing service function allocation for the service chain and showed that the service functions with independent sets can be parallelized to reduce the performance overhead in the cloud. Another study that has also been done is the use of SDN is to look at the performance analysis of SDN deployed in an ultra-dense network and satellite communication networks. And this work was done in the reference 1 here, where they examined the use of SDN to ease the management of ultra-dense sound with a distributed controller. And also in the reference 2 here, what we have is that SDN deployed in satellite network, SDN deployed in satellite networks was studied using a queuing network model. Now, in the first model, in the first reference, what they did was to propose a flow management model based on SDN and characterize the distributed controllers by considering the flow characteristics and outage. A work that is similar to what we did in this work is the performance analysis and modeling of SDN under BUSTI multimedia traffic, which is presented in this reference 1 here, where the authors use a Markov modulated Poisson process to investigate the performance of SDN in the presence of BUSTI and correlated arrivals. However, they assume that the packet arrival process from the Markov modulated Poisson process Q is also a Markov process modulated, is also a Markovian to allow for a tractable analytical model. But unlike them, what we did was to consider software-defined networks, although it has a similar, the network traffic in the data plane also have a similar characteristics with the network traffic considered in this work. But unlike them, we used the results from the reference tool here to better model the packet's arrival at the control plane. So in general, in contrast to all the works here, we use the QE network model to analyze the behavior of network traffic in software-defined industrial control networks. We consider the strong periodic pattern of network traffic in industrial control networks and approximate the arrival process using a Markovian modulated Poisson process. Also, we use the work from the second reference to obtain a realistic characterization of the interaction between the data plane and the control plane. We then apply the analytical model to study the effect of adversarial flow in software-defined industrial control networks. So let's look at the system modeling. We considered, for the system modeling, we consider software-defined industrial network proposed by Ahmed et al. So in the network they proposed, as depicted in the diagram here, what we have in the data plane consists of Raspberry Pis, sensors, and actuators. The Raspberry Pis are used for receiving packets from the sensor and instructing the relevant actuator to take actions based on the respective flow retrieved from the flow table and also the corresponding controller. An existing flow is retrieved from the flow table while a new flow is sent to the controller via a packet in message. On getting the packet in message, the controller instructs the Raspberry Pi on how to forward the flow via a packet out offload mode message. An interesting feature that deserves to be mentioned here is the nature of data plane traffic. Many recent studies have shown that network traffic in industrial control networks exhibits strong periodic patterns. They are usually bursty and cannot be properly modeled by Poisson arrival process as done by several other authors. So what we did is to use a Markov modulated Poisson process to capture the time varying arrival process. This allows us to model or to derive the analytical model as an infinitesimal generator matrix Q of the Markov chain and the arrival matrix, which all can then be characterized using the formula we have here, where the P1 is the transition rate from state 1 to state 2, and the second is the rate out of state 2 to 1. Then the lambda 1 and lambda 2 represent the traffic rates when the Markov chain is in state 1 and state 2, respectively. We can then obtain the average rate of arrival rate of network traffic using the formula showing on the slide. So now this is the QE network model that we applied to study the performance and also to evaluate the adversarial actions in industrial control networks. The arrival process of packet at the data plane of the SDN in industrial control network consists mainly of the network traffic that is modeled using the Markov modulated Poisson process. Then for the controller, we consider the case of multiple controllers. Multiple controllers are usually employed for redundancy, such that if one of the controller fails, another one continues to work in a state. And also there is a synchronization mechanism which the controllers use to ensure that a failure of one does not affect the entire functioning of the network. However, the control mechanism, the synchronization mechanism, was not considered in this work. For the arrival process at the controller, it's actually the departure process of the switch. Now, to obtain, since we are using the results from TN, as mentioned in the previous slide, the arrival process at the controller would become a Poisson process instead of a Markovian arrival. Then this would enable us to use MM1Q, which means a single server that has a Poisson arrival and exponential service time. Then let's consider the probability of an arriving packet that is new is given as P. And the probability that it's not a new packet is given as 1 minus P. Now, from the queuing network model shown in this figure, an arriving packet at the data plane is checked to see if it belongs to either an existing flow or is a new flow. The probability that the arriving packet is a new flow, as mentioned, is given as P. And if the packet is a new flow, the packet is sent to the controller in order to obtain information on how the packet should be forwarded. In the case of an arriving flow belonging to an existing flow, the packet is forwarded without consulting the controller with a probability of 1 minus P. So let's look at the performance measures. So let's TS be the forwarding time of packets through the data plane, and TC be the forwarding time of packets through the control plane. So to obtain the total forwarding time of packets through the entire queuing network, this can be divided by the forwarding, but packet forwarding, it can be divided into two cases. Now, the forwarding without the intervention of the control plane and the forwarding with the involvement of the control plane. The latter consists of surgeon time of the packet, that is the expected time that the packet is going to spend in the control plane, whereas the former is the expected time, the surgeon time of packets in the control plane. So we just have that the total packet now. With this now, we can now derive the formula for the total time the packet is going to spend in the entire network using the formula showing on the screen. So the value of TS, which is the average surgeon time of packets in the data plane, can be calculated using the method proposed by Fishin and Meyer-Heston, which was taken from this reference here. Now, using the results from TN, as I said, it showed that the departure process of a Markovian arrival is not Markovian, but rather it becomes a Poisson process. Hence, the arrival at the control plane can be obtained using the formula shown here, And we can then derive the value of TC, which is the average sojourn time in the control plane, using Little's law. Is the standard formula that is used to obtain the average sojourn time for MM1KQ. So let's look at the evaluation that we performed to see how an adversarial actions could affect industrial control networks. To investigate the effect of adversarial flow in software-defined industrial control networks using queuing network, what there are some few assumptions that we had to make. The first is that we had to assume that the attacker has some probabilistic knowledge of the regular traffic. And also, we have to model the adversarial flow by aggregating the adversarial flow and the regular flow. Then, using his probabilistic knowledge of the regular flow, the attacker can then, we then observed how an attacker may vary the arrival rates of the regular traffic to increase the average sojourn time of the traffic in the entire network, leading to a breach of quality of service requirements. The main objective of the attacker is to cause a denial of service attack. In order to model the adversarial flow, there are different hierarchies of models that may be considered. These hierarchies of models would be based on how much knowledge the adversary is using to formulate the adversarial flow. For the first level, it involves the superimposition of adversarial flow and the regular flow. And in the second level, a stochastic model of the legitimate traffic can be used for modeling the adversarial flow. And in the third level, it involves the use of actual observation of the regular traffic for modeling the adversarial flow. Although the hierarchies of models describe a spectrum of how much information the attacker would have in order to formulate the model to be used to attack the entire network, we present the first level of this model in this work to be able to show the utility of our model. And the first model has to do with the aggregating the regular traffic and the adversarial traffic as shown in this diagram. So what we have now would be that the arrival rate of traffic to the queuing network model is then the ratio of the arrival rate of the regular traffic and that of the adversarial flow, which is under the control of the attacker. The purpose of this evaluation is to study the effectiveness of adding an adversarial flow in bridging the quality of service requirement. And to do this, we had to parameterize the queuing network model by first assuming that the traffic rates of regular traffic are the same as that of the traffic rates of the adversarial traffic. This would allow us to examine how an intelligent attacker may manipulate the arrival rate of the adversarial flow against the regular traffic in such a way that the probability of bridging the quality of service requirements is high. Because an explicit estimate of the combined traffic is combined such that we take the regular traffic and express the adversarial traffic as an addition with some probability of extra traffic. Now look at it, some of the parameters we used for the study. First, we assume that the service rate of data plane is the same as that of the control plane. The infinitesimal generator of the Markov modulated Poisson arrival is set at 0.6 and 0.03. And we use the same buffer for the data plane and the control plane. We then employed the results from Jack Chirac et al. That showed that the probability that an arriving packet is a new flow is equal to 0.04. We use this as a worst case scenario. By varying the arrival rate of the adversarial traffic against the regular traffic, what we did was to observe under what condition will the adversarial traffic increase the overall average sojourn time of network traffic in the network in order to breach the quality of service requirements of the network. So some of the results we obtained. In this scenario that we described, an attacker with some knowledge of the regular traffic can increase the average, his arrival rate, the arrival rate of the adversarial traffic in order to increase the average sojourn time of traffic in the network. This is depicted in the result in this diagram we have here. You can see as the adversarial traffic increases, the average sojourn time also increases. So an attacker, it's possible for the same attacker to continue to increase the arrival rates of the adversarial traffic in a stealthy way in order to avoid detection until it causes the network to breach the quality of service requirement, thereby leading to a denial of service attack. What can we infer from this result? We can infer that from our study that the probability of breaching the quality of service requirements of network traffic in software-defined industrial control network would increase with a knowledgeable attacker. Although there are more clever ways of modulating the adversarial traffic than the simple superimposition with some knowledge of the irregular traffic that we presented here. What we did was to use this idea to show the capability of an intelligent attacker. So to conclude this presentation, research in the applicability of SDN for industrial control networks is still ongoing, and consideration for a situation where adversarial actions could occur is still very pertinent. What we have proposed in this work is an analytical model using a queue network model to study the behavior of network traffic in software-defined industrial control networks. We also derived the performance measures of an analytical model and then applied the model to study the effect of adversarial flow in software-defined industrial control networks. There are several directions for future research within the analysis of SDN using software-defined industrial control networks using a queuing network model. One direction is to layer a particular application domain on top of the queuing network model. For example, it is possible to consider the condition under which an adversarial flow in software, an adversarial flow in SDN deployed for IEC 61850 substation could breach the performance bounds as specified by the standard. Another direction is to investigate refinements of the probabilistic density function of the regular traffic and to derive its performance metrics. This could be referred when the regular traffic is combined with the adversarial traffic to study the effects of adversarial flow. That has been all for me. Thank you so much for listening. You're welcome to ask me any question.